So I'm going to do the problems from workshop 9 just quickly. I'm not going to, as usual, put the text of them in, so you'll have to follow along with your own copy of the problems. So on number 1, there we go. Number 1, you're asked to find the smallest value of n such that Sn approximates such that Sn, the partial sum up to n, approximates the sum of the series within 0.001. So recall that we know that S minus Sn, in other words, the difference between the true value of the series, that's true, and this is approximate, the difference between them is less than a n plus 1 for an alternating series, such as the one that we have here. Therefore, we know is that we want to choose an plus 1 to be less than or equal to 1 over 1000. That's 0.001. The reason we want to choose an that way is that we know that if we can get an to be at least that small, then that means that this statement will be true. So what I want to do is set up equation, let's see, 1 over n plus 1 squared plus 7 should be less than or equal to 1 over 1000. That means that n plus 1 squared plus 7 should be greater than or equal to 1000, because inequalities work that way. We now say, let's see, n plus 1 squared is greater than or equal to 993, subtracting 7 from each side of that inequality. I then get n plus 1 is greater than or equal to the square root of 993, which is approximately equal to 31.5. I subtract 1 from each side of the inequality. That means that n should be greater than or equal to 30.5. And since you can't add up a fractional amount of a term, you have to go with, in order to make sure that you have enough terms, you're going to have to go with the next integer. So this means that n is equal to 31. I want to be clear about something, because I know that some of you are going to say, well, wait a minute, I know that if I get a number that's somewhere in between two integers and I'm asked to round, there are all sorts of rounding rules. Maybe 0.5 could be rounded down instead of up. I know by default we round up. If you think this way, you're trying to apply some sort of rote recipe from a previous class rather than really thinking about what you're doing. Estimates get more accurate the more terms that you have. We already showed that in the lecture and in the previous workshop. What that means is that if I were to round down, in other words, even if I got something like 30.1, you'd say, oh, well, the nearest number is 30. That's beside the point. The point is that 30 is going to be a less accurate estimate than 30.1. And you want one that's at least as accurate as within 1 in 1,000, which means you have to go up to the next integer. So even if you got, say, 30.000001, the correct answer would still be n equals 31. So for problem 2, I've put up the series. It's actually more of a polynomial. It's supposed to hint at the idea of what a Maclaurin series is. So we see that m of x, as I've defined it, is f0 plus f prime of 0x plus f double prime of 0 over 2 factorial x squared, etc., etc., etc. By the time you've done this problem, presumably you've memorized the formula for Maclaurin series. So the point of this was to try to demonstrate, just to get you to work through the algebra, showing why this formula works. The reason it works, of course, is that it makes all of these, it makes all the derivatives equal to the original function f, provided that we're only evaluating them at 0. That's the nature of Maclaurin series. We went over kind of the rationale for this in the lecture on Taylor and Maclaurin series, but I'll just do the calculation. If I take the first derivative, f of 0 is of course a constant. Don't be fooled by the fact that it's a function. It's a function that I'm evaluating at a constant, so f of 0 is a constant. So when I take the derivative, I get m prime of x is equal to f prime of 0 plus, for the second term, I take 2 times 2 factorial, and that just cancels out because 2 factorial is 2. So that gives me f double prime of 0 x. Here I have 3 over 3 factorial. So that's going to give me f triple prime of 0 over 2 factorial. And why is that, by the way? 3 over 3 factorial is equal to 3 over 3 times 2 times 1. So those cancel, giving me 1 over 2 factorial. That's just kind of how that sort of division works. So this is going to be x squared, and then I have f fourth derivative of 0. 4 over 4 factorial gives me 3 factorial x cubed, and then plus f5 of 0. 5 over 5 factorial, you can see the pattern now, that gives me 4 factorial x to the fourth. So that's m prime of x. That means that m prime of 0, as we can see, if I plug in 0 for all these x terms, then everything you see with an x after it is just going to disappear, leaving me with f prime of 0. And that's the whole point, is that m prime of 0 is equal to f prime of 0. So now, I'm sorry, that was actually b. I put less care into these workshop recordings so that I can do them without editing, so you won't get the polished version. I'm sitting here reading it with the paper next to me. So m of 0 is just going to be f of 0 for the same reason, because all of these x terms simply disappear when I plug in 0. So okay, so I found now m of 0 equals f of 0, m prime of 0 equals f prime of 0. What we can see is that if I keep going and find the remainder of the derivatives, I get m double prime of x. I'm going to take the derivative of m prime. That's going to mean that f prime of 0 is just a constant, it disappears. I get now f double prime of 0 plus f triple prime of 0x plus f4 of 0 over 2 factorial x squared plus f5 of 0 over 3 factorial x cubed. Notice what's happening here to these terms on the end. The number of the derivative, f4, f5, those stay the same, but this factorial and the exponent keep reducing by 1 every time I find the derivative. So let's keep going. M triple prime of x is equal to f triple prime of 0 plus f4 of 0x plus f5 of 0 over 2 factorial x squared, and 4 of x equals f4 of 0 plus f5 of 0x, and then of course m5 of x just equals f5 of 0. So we can easily see now that if I plug in 0 into any of these, I just get these terms because all the others have an x after them and they disappear. So that gives me m double prime of 0 equals f double prime of 0. M triple prime of 0 equals f triple prime of 0. M4 of 0 equals f4 of 0. And m5 of 0 equals f5 of 0. There we go. So what should the discussion of this have looked like? Because I asked you to discuss this in your group and try to write up a description. The point is that the function m we'll go back here and see the function m of x as I've defined it has its value and its first five derivatives are equal to the value of the original function and its first five derivatives as long as we evaluate them at x equals 0. So at x equals 0, m and f have the same value, slope, concavity, as well as the things that the next couple of derivatives represent. That's the third, fourth, and fifth derivatives are called jerk, snap, and crackle. So that's so you have I wouldn't expect you to necessarily describe it in these terms, although I did cover it in the lecture. Um, just understanding that the derivatives have the same value at have the function and its derivatives all have the same value at x equals 0 is good enough. But if you wanted to describe it qualitatively, what you'd say is that the function and its derivative is what you'd say is that the function m and the function f at x equals 0 have the same value, slope, concavity, jerk, snap, and crackle. And if you think about what this would mean in terms of, where's my pen not working? If you think about what this would mean in terms of the function itself, what that means is that if I were to draw these functions, let's say at x equals 0, what we're going to see is that at this point, the function, if this is, sorry, if the blue function is f of x, imagine that I'm drawing the function m of x in red. Think about what it's going to have here. It's going to have the same slope. In other words, the tangent line to both functions is the same. It's going to have the same concavity. Look how the functions are bowed inward at roughly the same sort of curvature at that point. It's a little harder to draw what the third, fourth, and fifth derivatives mean, but the point is that they all have to be the same at that point. So that's what you're looking for when you look for the relationship between a function and its Maclaurin polynomial, is it's going to have certain agreement at the center in derivatives up to whatever power I have in the polynomial that I use. So for number 3, we have f of x is equal to 1 over 3 minus 5x squared. So the first question is to find the Maclaurin series. Now, let me point out what mistake number 1 that people make. Mistake number 1 is people say, oh, I just saw this lecture on Maclaurin series and I see that Maclaurin series is defined this way. And they say, let me try to use that formula. That would be a complete mistake here. I mean, it commits what I consider to be the greatest sin in all of math classes, which is it's an inelegant solution. It's not that it won't lead you to the correct answer, it's that it would be very complicated to do. The correct point to understand here is that for a given center, such as c equals 0, there is exactly one power series corresponding to any given function. So if you find the power series by any method at all, then you have found the Maclaurin series for that function. So that means that we can do this the way we did in the previous section by geometric expansion. So here, just observe that 1 over 3 minus 5x squared is equal to 1/3 times 1 over 1 minus 5x squared over 3. So that's going to equal 1/3 times the sum from n equals 0 to infinity of 5x squared over 3 to the n. Simplifying it a bit more, that's going to give us 5 to the n x to the 2n over 3 to the n, and then finally I want to bring this 3 in the denominator back into the series, so that becomes n equals 0 to infinity of 5 to the n x to the 2n over 3n plus 1. So that's the Maclaurin series for this function. Now, B, we're asked for f27 of 0 and f28 of 0. Once again, if you're the type of math student who likes to sort of applying formulas, you're going to say, okay, I guess he wants me to differentiate this 28 times. Of course not. Of course, that's not the point here. The point is to use what we know about Maclaurin series. Since we've found that this is the Maclaurin series, note that a Maclaurin series looks like this. It has f of 0 plus f prime of 0x plus f double prime of 0 over 2 factorial x squared plus f triple prime of 0 over 3 factorial x cubed. Just to make it clear, that's a 2. So take a look at this. The nth derivative, in this case the third derivative, is always part of the coefficient that's attached to the third power, to the nth power. So it makes sense that if I keep going, what I'm going to get is some term that looks like f28 0 over 28 factorial x to the 28. So whatever the coefficient is of x to the 28th has to be equal to this if it's a Maclaurin series. So let's see what coefficient is going to be attached to x to the 28th. I'll do the 27th next just because it's a little, it requires one more step to understand. So if I plug in n equals 28, then since this is going to be x to the 2n, I would get x to the 56th. That's not the term I want. I want the one that's the 28th power of x, because it's always the 28th power of x that's going to have the 28th derivative next to it. So what I want to do is plug in n equals 14. That's going to give me 5 to the 14 x to the 28 over 3 to the 14 plus 1 is 15. So this is the term that has the 28th power of x. So whatever the coefficient is of the 28th power of x, let me put this in red, this thing here has to be equal to the 28th derivative evaluated at 0 over 28 factorial. So I can simply equate them with each other. f28 of 0 over 28 factorial is equal to 5 to the 14th over 3 to the 15th. And so that means that by simply multiplying both sides of this equation by 28 factorial, I can get f28 of 0. So f28 of 0 is equal to 28 factorial times 5 to the 14th over 3 to the 15th. There we go. Okay. So that's the 28th factorial. Now what about the 27th factorial? Well, some people might say, well, why don't we just plug in 13.5? But you can't do that because this is a series, and the indexes are always integers. So there is no 13.5 term. This is kind of the point. This is a series that's going to look like this. If I were to expand this series, what it's going to have is, let's see, that's going to be 5 to the 0, x to the 0 over 3. So that's going to be 1/3 plus 5 over 9 x squared, because when I go to n equals 1, now I get x to the 2 times 1, which is 2. The next one is going to be 25 over 27 x to the 4th, because now I plug in n equals 2. And n equals 2, I have x to the 2 times 2, which is 4. So notice that I'm skipping all the odd powers of x. Well, what happened to them? Well, they simply have 0 coefficients. You can rewrite it this way. 5 to the 9th x squared, 0 x cubed, 25 over 27 x to the 4th. And it looks like that. And you see, so all the odd terms have a 0. Well, that means that 0 using again this aspect of the formula, that means that 0, since we assume that from this pattern that we're going to have 0x to the 27th, that means that 0 must equal x to the f to the 27th derivative of f evaluated at 0 over 27 factorial. That means that f 27 of 0 is equal to 0 times, not 2, 0 times 27 factorial, which is just 0. So the answer is that f 27 of 0 is equal to 0. So there's our two answers to part B. Okay, part C. Let's use the results from part A to find a power series for 10x over 3 minus 5x squared squared. Okay, so how are we going to do this? The thing to note is that the original series that we have, it was 1 over 3 minus 5x squared, right? So the derivative of 1 over 3 minus 5x squared over 3 minus 5x squared is equal to, surprise, 10x over 3 minus 5x squared squared. Okay, let's actually rewrite this a little bit. Sorry, I just want to rewrite this different way, in a different order. So 10x over 3 minus 5x squared squared is equal to the derivative of 1 over 3 minus 5x squared. So that means that it must be equal to the derivative of the sum from n equals 0 to infinity of 5 to the n x to the 2n over 3 to the n plus 1. Why? This is, again, one of the very, very, very important points of this work on Taylor and Maclaurin series. A Taylor and Maclaurin series stands in for the function. Any place that I can use the function, I can use its series. So that means that if I can find this function by taking the derivative of this function, then I can find a series for this function by taking the derivative of the series for that function, because this and this mean exactly the same thing. This is the main innovation of the end of this chapter, is that a function has a corresponding series that can replace the function. So that's going to equal, I'm just going to find the derivative with respect to x using the ordinary power rule. That's going to equal the sum of 2n times 5 to the n x to the 2n minus 1 over 3 to the n plus 1. We know we're counting up to infinity. The only thing is, we don't want to start at 0 because then I would get a term of negative 1, and we know that the derivative of x to the 0 is not x to the negative 1. X to the 0 is just a constant, its derivative is just 0. So I'm going to actually start this at n equals 1 so that I can bypass that negative 1 term that I would get. So this is the series for this function. And now for the next part of the problem, we want to find a series for 1 over 3 minus 5x squared squared. So that's going to equal 1 over 10x times 10x over 3 minus 5x squared squared. That's just simple algebra. And since we know that we have a series for that, that's going to be 1 over 10x times sum from n equals 1 to infinity of 2n times 5 to the n x to the 2n minus 1 over 3 to the n plus 1. Now, dividing this out, I want to apply this. I'm going to bring the 10 in the denominator into the series. So that's going to be 2n times 5 to the n over 10 times 3 to the n plus 1. And I want to divide out 1 power of x. So that's going to be x to the 2n minus 2. Now, it's often common to write this is a perfectly good way of writing the series, but it's often common to try to clear out this sort of awkward exponent on the x. So it would also be correct to write this as the sum from n equals 0 to infinity of, if I'm going to start at 0, then I have to advance n by 1. So that's going to be 2 times quantity n plus 1. So 2n plus 2 times 5 to the n plus 1 x to the 2n over 10 times 3 to the n plus 2. So that would also be an answer. So let's do the last problem, number 4. We want to do is write a series for e to the negative x squared, at least write the first 3 non-zero terms of that. So recognize that e to the x is equal to 1 plus x squared over 2 factorial plus dot dot dot, but I just need the first couple of terms. So the thing to do is, again, a very common mistake is to say, I know the formula for Maclaurin series, let me just keep differentiating this and keep applying the formula until I see the pattern. That would be a mistake. You already know the series for e to the x. All we have to do is treat this as a composite function. Every place you see an x in this series, just replace it with negative x squared, because that's how series work. So that means that e to the negative x squared is equal to 1 plus negative x squared plus negative x squared squared over 2 factorial. That equals 1 minus x squared. Negative x squared squared is positive x to the 4th, so that's plus x to the 4th over 2. And then plus dot dot dot, but we're only asked for the first 3 non-zero terms. Okay. Again, the point here that I'm trying to make is that a series can replace the function. You can try as hard as you want to find an antiderivative of e to the negative x squared, and you can't do it. It's provably true that there is no elementary antiderivative for e to the negative x squared. There's a way to write it, but it involves additional functions that we haven't learned about yet. There's no way to write it in terms of what you normally think of as antiderivatives, like products and quotients and sums of things like, exponential functions, power functions, sine, cosine, and tangent. There's no way to write it in those terms. So the best we're going to be able to do is to find some approximation. The idea is that this very simple polynomial is approximately equal to e to the negative x squared. That's the whole point of saying that it's the series or Maclaurin polynomial for that function. So that means that this integral should be approximately equal to the integral from 0 to 1 of 1 minus x squared plus x to the 4th over 2. And of course, this is a problem that is too easy almost to be part of a Calc 2 course once you've set it up that way. So that's going to be x minus x cubed over 3 plus x to the 5th over 10. And we're doing that from 0 to 1, so that when we plug in the zeros, we're just going to get zeros. So this is going to be 1 minus 1/3 plus 1/10. Finding a common denominator of 30, I get 30 over 30 minus 10 over 30 plus 3 over 30. And that gives me 23 over 30. So that's the approximation that we're looking for. This is if I can sum up what the point of this workshop is, it is that the Maclaurin series, or in a shorter sense, it's the Maclaurin polynomial, stands in for the function. Any place you can use, any place you can use a function, you can use its Maclaurin series in its place. Or more generally, if you want to choose a different center, you can use its Taylor series in its place. Go back to Calc 1. I know this was a topic that many people found quite difficult where we did linear approximation. We used a tangent line at some arbitrary point A to replace the function, and you get an approximation. We're just doing a more accurate version of that when we use a Taylor or Maclaurin series.